So let me share your content. Okay, view, zoom, not zoom, full screen. Okay, awesome. So first of all, for the line people, let me know if you can't hear me or if you cannot hear us. Okay. So well, it's a great pleasure to have Evženie Čoupková here. She's a fourth-year PhD student in mathematics at Purdue University. She is advised by Mirel Coutin from the School of Electrical Engineering. Her PhD work is on theoretical machine learning. She uses different tools from reanalysis and probability theory to say something about generalization error of algorithm. As you know, probably the main goal of machine learning is having good generalizations, namely having good performance on C instances, and it's also good to have some theoretical results about those things. And she works on that. In particular, today she's going to talk about one-dimensional random projections and how good these algorithms are. Okay, so I'll let Evženie start her presentation.
Thank you very much for the introduction. Thank you for invitation, Professor Saratella. Thank you very much for coming, and online as well. So yes, today I would like to present a joint work with my advisor, Professor Mirai Bhutan, which is optimality and complexity of classification by one-dimensional projection. So what we did was we took a very simple algorithm for classification, in which had a very good empirical properties. It was tried on some image data sets, and surprisingly, it had a good performance. And we wanted to analyze it theoretically. So let me first introduce the algorithm. Okay. This is a binary classification of potentially high-dimensional data. We consider data in RD, where D can represent number of pixels in the image of other quantity that describes our data point. We have labels for those data points, yi, and we assume that they're either -1 or 1. So it's a binary classification. We do not consider multi-class classification. And we would like to train our algorithm on a training data set and then apply it for a new data point to see if it belongs to class -1 or 1. In order to do that, we generate n vectors from uniform distribution on the unit hypersphere in RD. N is a parameter of our algorithm. We decide how large n will be before we apply it. And after generating vectors, for each vector, we project the data points onto this vector using dot product. And we get a one-dimensional feature Zij. And we classify those features in one dimension by finding an optimal threshold, Tj. The next step is to compute the error of this classification in one dimension and see which projection direction resulted in the smallest error. And the projection direction that resulted in the smallest error will be our final classification projection direction together with the optimal threshold in this projected space. So this type of classification results in a very simple boundary between classes. Do you have an idea what might be a boundary if we classify it this way? What's the type of the?
Like something linear.
Yes, it's a hyperplane. So it's a hyperplane in space RD, which might be optimal for some data sets, which are, for example, linear separable. It might be also optimal if we assume that the data come from some probability distribution. And if we consider, for example, a mixture of two Gaussian with the same covariance matrix, then the optimal decision, the best theoretical decision we can make, which results in the bias error, is a hyperplane. So in those cases, a hyperplane would be sufficient for a good classification. But we wanted to add a little bit of flexibility to our model so that we can have some more complex boundaries that are able to classify well even the data sets which are not linearly separable, for example. And in order to do that, we consider a polynomial extension of the original features of order k. So for example, if we have two-dimensional features, x1, x2, and we decide that we will extend it to the order 2, then we will take x1, x2, x1, x2, x1 squared, and x2 squared. And these will be our extended space with extended features. And then we follow the same recipe, generate n random vectors, but now in the extended space. So it will not be in dimension 2, but in dimension 5. That actually corresponds to a polynomial which has random coefficients. And we choose a threshold for the polynomial to decide which class belongs where. That means that the boundary between the classes becomes a zero set of a polynomial.
So you fix small n, correct, a priori.
A priori.
The small n for the number of vectors you use is.
In order to use the method, yes. In order to do the theoretical analysis, we then considered what happens when n converges to infinity. So our second part, the first part of the paper considers the generalization error of the algorithm, and the second part considers the accuracy, the approximation properties of the algorithms, and our theoretical results for the approximation consider what happens in the limit when n converges to infinity. Okay, and we asked ourselves what are the special properties of such a simple classifier. And the first thing that we considered was the generalization error. Generalization properties, abilities of the algorithm. So when we train on a data set, we usually get a small error, or we want to get a small error, but then the question is, if we take a new, totally different data set, are we going to get good results, or what would be the accuracy in the future? In order to answer that question, we can focus on the hypothesis set. Here we denote it by F, and this is the set of all the functions, and for binary classifications, those are binary values functions that we choose from when we classify. So the process of classification can be viewed as choosing a function from that set. Sometimes it's a parameterized set, so we consider all of the functions that have a special form and some number of parameters, and we choose the parameters that would fit our data best. But sometimes we do not see that explicitly. For example, for neural networks, we just build an architecture. We decide a number of layers, decide a number of nodes in each layer, and then train it. But by deciding the architecture of the network, we also fix the family of functions from which we choose. So there are some parameterization hidden in the process. And the choice of the function usually follows an empirical risk minimization process when we take our data set, compute the loss on the training data set, and choose a function f out of our family such that the error on the set is minimized. Here we consider the easiest case of the 1-0 loss. So we just count all of the cases when the classification by function f does not correspond to the true label, and we divide by the number of samples in the data set. But if our family is too large, we can push the training error to 0, actually quite easily. For example, if you consider that f contains a function that gives 1 to all of the points in the training data set that have 1, and 0 everywhere else, we get a training error 0. But is it going to be good for a new data set? Perhaps not. So in order to see if the algorithm is good, we would like the population error to be small. And here we assume that the data come from some probability distribution. We assume that our data come from some probability distribution, and we can compute the probability of error for each point. So this is the next line. Here we integrate over all of the points we have, over all of the labels, and we see what is the probability that this point will have that label, and we integrate the error. And that the main goal for us should be to minimize that population error. But we cannot compute it because we usually do not know what the distribution is of our data, the underlying distribution. What we can do is to bound a generalization gap. And generalization gap is this quantity where you subtract the population error for each function and the training error for each function, and take the supremum over all of the family F. Now, this is a random variable because this error is given if we know the probability, but this error is random. Depending on the data set we have, we will get either larger or smaller error on using F. So there are two ways how to approach the generalization gap. We can either say that it is smaller than some quantity with a large probability, or we can examine what is the expectation of that random variable. And that is where I go in the next slide. We would like to see what are the bounds for the expected value of the generalization gap, how far the training error is from the population error. A known result is that if our set F has a VC dimension DVC, then we can bound it by square root of 2 ln 2n plus 1 over n, and there's DVC for the 2n plus 1. Large n is number of samples. DVC is VC dimension of the set F.
Maybe define
the VC dimension. Yes. So the VC dimension is some kind of a combinatorial quantity that says what is the largest number of points such that these points can be shattered using our family. And shattering means that if we assign any labels to the points, so for any assignment of the points, 0, 0, 1, or minus 1, minus 1, 1, minus 1, minus 1, minus 1, we will always find a function in F, in large F, that separates those points perfectly. And yes, for example, for the linear separation of the data points, the VC dimension is D plus 1, when D is the dimensionality of the space of the data. What we show in our work is that the bound on the generalization gap for thresholding after random projection does not depend on the VC dimension, but it can be expressed using the number of projections that we use. So here, the small n is the number of projections that we use, and large n is the number of samples that we have. Both of these bounds actually show us that in the case when VC dimension is less than infinity, or in the case, in our case of thresholding after random projection, the learning is actually achievable idea, because the bound goes to 0 when the number of sample increases, which means that if we have a large amount of sample, we can guarantee that the training error will not be far away from the population error. So this is just a plot of a comparison of the two bounds from the previous slide, where we have the bound for VC dimension 2, it's in orange, the bound for VC dimension 3 is in green, and the curve for random projection. On the horizontal line, we have number of projections that we use, So it varies from 1 to 1,000. And on the vertical line, we have the error between the population and the training using 10,000 data points. So here we see that the bound that uses VC dimension, it does not depend on n, so it's just a number, but we compare it to the to the random projection bound, which actually increases with n, but it increases very slowly, and it's smaller than even VC dimension equal to 2. And I would like to note here that VC dimension equal to 2 corresponds to a very low complexity classifiers, because it means that, for example, linear classifiers of one-dimensional data, so really small.
So what is the x-axis here?
Here?
Yeah.
Number of projections. And so as you can see, oh, I don't know if I can go back. Yeah, here. As you can see here, the bound depends on the number of projections.
So what is with low n after a certain you don't need too many projections to have the maximum classification.
It's a tricky question. Actually, it depends, for example, on K. If you want to extend your data a lot.
K, you mean the dimension of the data set?
No, the dimension of the extension. It depends as well on the dimension of the data set, D. So if we want to target a certain accuracy of the algorithm, then we might need to extend using K. And the larger K is, the larger N is. And if our data is highly dimensional, if D is larger, then N also grows. So at some cases, N will be very large if we want to achieve some accuracy. I have a slide in the end of the D plus K.
Namely, with respect to the dimensional sets of features, the set of features that you use, I expect n to not be that large.
That large.
So I believe that it might increase with k. I think it might be that after a reasonable, very small fraction of the number of features in total that you use. So I mean, I expect that n is reasonably small with respect to the dimension of the feature space.
It depends on the data. So for example, if you have some data with which are very sparse, then n does not have to be large. You can just like separate them easily using like a range of directions.
In a different way, it seems to me that the plot that you have, I would guess, is kind of a generic. The fact that it grows relatively quickly, it's kind of generic, in the sense that whatever the other parameters you use, there's going to be always something like increasing very rapidly at the beginning, and then kind of
flatten out.
So, sense of and then the optimal, let's say n, be chosen at n with the highest curvature. I don't know what it. So when it curves the most, right? Let's say that the second dot to me looks like the best n. Right? In the sense of when the moment in which you start to not
increase that
much by adding other vectors. The reason why I'm thinking there is in concrete, when you have when you try to maybe have a good classification accuracy, let's say you have brain imaging or some very high dimensional stuff, and you want to really have good accuracy. People use I use very complicated algorithms to try to get very good accuracy, very good. Watching a movie, have the brain structure. I just analyze that. I want to say what the person is seeing based on the neural activity. But then it's very, very high dimensional, right? So I'm just thinking if that sense, having a small number of projections that are good enough for something like a low dimensional representation, it's very useful in general, right? So and knowing what is the smallest amount of projection for which to reach a level of accuracy which is not that far by the optimal accuracy you can get, it's kind of very useful.
Yes. It also can be used as a benchmark. So for example, before starting using a very complex algorithm for which you might know, like the generalization gap might be high, right? The more complex the algorithm is, the larger is the generalization gap in theory. So before using that, you can just try to project, see what the accuracy is. And if it's good enough for you, then first you have a very simple algorithm. And second, you know that the generalization gap will be small because you don't choose from such a
for this type of model, it is true, right, that you want to have that you're going to have a performance which decreases without too many variables, right? For this type of algorithm, if you increase the number of variables too much, you sure you're going to have a decrease in performance for this type of algorithm.
Yeah.
So if you that k that you use to enlarge the original data set, you increase that k too much, the accuracy is going to decrease 100%. That's the point. So I believe that. Sorry for interrupting.
No, it's okay. I'm glad. Okay, so that's the proof of our result. Is actually this is our first result, and the proof is very straightforward. It is based on the key notion of the growth function of the class f. So again, we're starting with our family of functions f. And we define a growth function. The growth function gives you a number of dichotomies, a number of different labelings that your function set is able to achieve. So if you have, for example, 3 points, overall there is 2 to the power of 3, 8 options that may be covered by the binary classification. And the method of random projection does not cover all of them. It covers, so since we are thresholding at some point, after one projection, we can get either 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, or 0, 0, 0. But we will never get 1, 0, 1 or 0, 1, 0. So some of the dichotomies are missing. And in our case, the number of dichotomies for one projection will be always smaller or equal to 4n. When we have n projections, we have the bound that after each projection we have new 4n dichotomies for 2 endpoints. So it would be 2 for small n, large n dichotomies. And there exists a result that says that the generalization gap can be bound by 2 ln, and then there's 2 of the growth functions of 2 endpoints. And if we replace the growth function by our bound of 4 and n, we get our result. Usually what is done is that the growth function is bounded from above by using a VC dimension. So using Sauer-Shannon lemma, we know that the growth function, which is smaller or equal than this number, I'm sorry for the typo, will be smaller or equal than a polynomial of degree dvc. So if we replace it in here, we get the classical result. So what we are using in our case is that the Sauer-Shannon lemma is not tied for one-dimensional classification, binary classification, and yeah, we only have a very low flexibility in the dichotomies that we can choose. But there exists a better bound for the generalization gap, a classical one, which is on top of this slide. Here, we get rid of the logarithm of the number of samples term at the top. And for quite large n's, or asymptotically when n goes to infinity, this is a better bound than the previous one. So this bound is a little bit more deep. It does not only count the number of dichotomies that we get, but also the structure of those dichotomies. So it is based on computing the covering number of the set of those 0, 1 vectors on the hypercube. And when we use the similar argument for the method of thresholding after random projection, we got a bound chaining argument, which is over here, which is tighter than the bound from the previous slide. It again depends on the number of projections n and on the number of sample points, large n. So here I would like to present a sketch of the proof, and it says that the generalization gap can be bound by this quantity when you have 24 over the square root of number of samples, and you integrate over logarithm of the covering number of the set of dichotomies, set of all the different outputs of our model. And R is the radius of the covering. And we integrate over R that goes from 0 to 1. For the method of thresholding after random projection, we use the fact that the structure of the dichotomies is also very simple. It's always in the line. So we either put a node, a data after projection, we either put the data point on one side or on the other side of the threshold, which creates a chain of dichotomies on a hypercube. And the covering number of this chain is small. So it's not possible that the dichotomies will be like all over the hypercube. They will always be in a line in this chain. And we can cover this chain using this number of covering points. And here is the comparison between what we need to integrate. This is the graph of what is inside of the integral in here, square root of logarithm. And this is comparison between what is being used for the VC dimensions, the typical function for the VC dimension equal to 2. And this is our step function, which we compute for the method of thresholding after random projection. So there is a certain gap again between the VC dimension and random projection estimate, which we use to create a tighter bound for this particular algorithm, which basically just says that the complexity of the family is very low. Okay, so that was the part about generalization. Do you have maybe any questions about generalization?
So about the gap, right? So was it that due to?
Why is it there?
Yeah. So
Okay, so I think I need to say something which
we
I'm
can,
not.
we can do it after if it's long, if it breaks.
The flow, what time is it?
Sure, it should be. We ask you at the end, right? Prefer to go.
Okay, let me go on. I'll think about that afterwards. So the second part of the presentation is about how accurate can actually this algorithm be. So even though the generalization gap is small, if our approximation is very bad, if our error rate is, I don't know, 70%, then the algorithm is not very useful. And in the second part of the work, we're showing that our algorithm is asymptotically optimal, meaning that with n going to infinity, the probability that we will find a good classification is large. It converges to 1. So there are two cases. We build a second part using those two facts. First, that the continuous function on a compact set. So for the approximation results, we needed to constrain ourselves on the compact set. For the generalization, we did not care about either distribution or, we didn't care about the distribution of the data that we had. It was universal. But for the approximation part, we constrained ourselves on a compact set. where we show that a continuous function can be approximated by polynomials with random coefficients. And polynomials with random coefficients is exactly what our algorithm will produce when we extend using K, when we extend using polynomial transformation. So it shows that given a function, a continuous function g and epsilon, there exists a K such that the probability that amongst n polynomials with random coefficients, we will find one that has a supremum distance from g smaller than epsilon. This probability converges to 1. And the second case, which will be useful, is that a binary function that splits the support in two measurable sets can also be approximated by polynomials with random coefficients on an arbitrarily large subset of the support. So if you have a function c that is binary and splits the supports into two measurable sets, epsilon larger than 0 and eta larger than 0, then there exists a subset of support which has measure larger than 1 minus eta. If 1 is the measure of the support, it can be scaled. Such that the probability that amongst n randomly selected polynomials, we will find one such that supremum distance from C on this smaller version of the support is smaller than epsilon converges to 1. So we need to restrict ourselves on the sub-support because there is a jump. Like if the function is binary, we need to cut off nearby the jump. And if we do that, then we can find a polynomial that will approximate that binary function well. And here we have the results for asymptotic optimality. We consider two cases. We consider the practical viewpoint when we have a training set, and we showed that there exists a K that with n converging to infinity, the training error converges to 0. And then there's a theoretical standpoint where we assume that we have full conditional probability knowledge. And we assume that the bias rule, which is the most optimal way to separate the data into two classes, the smallest error, which is not 0, always, usually larger than 0. So if the bias decision rule splits the support into two measurable sets, as k and n converge to infinity, the reducible error, which is the difference between our population error and the smallest possible bias error, this reducible error goes to 0. And here is something that perhaps answers a little bit one of your questions from the beginning. We examined how large n do we need in order to get good performance of this random projection algorithm. And here, there is a formula that depends on delta. Delta is the tolerance. So with probability 1 minus delta, we will get close to the optimal solution. And then there is d tilde. D tilde depends on d and on k. It's d plus k over k binomial. So it grows with d and with k, making n larger. But if k is theoretically, like let's say, second order polynomial is good enough for a small error, then we need n larger or equal than this quantity to get to that error that k guarantees, and it will happen with probability 1 minus delta. So it will not happen for sure because our projections are random, but we can say that with a large probability this will happen.
Again, what's the d tilde?
D tilde, binomial of d plus k over k. So this is basically d tilde is the dimension of the extended space. So if we start at 2, extend up to degree 2, then we have d tilde equal to 5. And then there is a comparison, a random projection and linear algorithm. And here we examine what actually happens when the dimensionality of the data increases. Because the VC dimension grows quite fast. The VC dimension is d plus 1. So if we have dimensionality of data 10, then a very simple linear algorithm already has VC dimension 11, which has quite a large effect on the generalization gap. Yes. Wait. It's not exactly exponential. It's more like linear in DVC, right? Because you're down from the logarithm. You have DVC and then logarithm of n over n, or just DVC over n if you use the better bound. But still, like it's much worse. It's exponential with respect to small n, because here we have DVC linearly, and here we have ln of a small number of projections n. And if you consider this graph, for example, you can see that this is VC dimension equal to 2. This is VC dimension equal to 3. You can imagine what happens with VC dimension equal to 11. And so we take a formula from the previous slide, how large n has to be to get close to the solution, as close as k allows us. Here we assume that k equal to 1 is enough, so that we don't need to extend our features at all. And we compute n. We assume that delta is 10%, like so with 90% chance we will get close to the needed accuracy. And you can see that n grows, and it grows quite quickly. You can see that for d equal to 10, we already have a pretty huge amount of random projections that we need in order to get close to the optimal bias decision. But n gets large, but the bound generalization gap is still quite small because there is a logarithm of n involved. And here Rfn, I did not introduce it in the previous part because there was not the direction that I chose in the presentation. But at first we analyzed the probability that the generalization gap will be larger than something. So Rf is the term with probability larger than 1 minus delta. The generalization gap will be smaller than this. And you can see that if you compare the linear algorithm, which is the last column, and the random projections still have smaller generalization gap. Even for d equal to 2, you see that it's smaller for random projection. But then for d equal to 10, it's almost half of the generalization gap for linear separation in the dimensional data. And linear separation is a very simple algorithm. If you consider neural networks, they have a much larger VC dimension than d plus 1.
Then those bounds are basically almost useless then.
Which ones? In the case, yes, that is the problem. That is the problem that is currently in theoretical machine learning. Like there are better measures of complexity than VC dimension. There is Rademacher complexity, which is not distribution free, and it gives better bounds. But basically, if I'm not wrong, most of these theoretical bounds are vacuous. So they give you something larger than 1, and then it's like, okay, so the generalization error, the population error will be arbitrarily large, even though your training error is small. So the question is what's happening there. And perhaps one interesting direction, which I've been thinking about quite a lot, is that the elements of probability actually reduce this bound. They reduce the VC dimension, they reduce the bound, and they can push it a little bit, but frankly, not that much. Like they push it down. For example, if dropout is used in the neural networks, then we consider the maximal VC dimension that the neural network has, but it will actually not be as big because we drop certain nodes out, and the the complexity of the set of functions gets lower. But still, yeah, the bounds are not applicable. Yeah. So this is the end of my talk. Thank you very much for your attention.
Thank you.
If you have any questions.
Okay, so let's see if there is anybody from the online audience which have questions.
Hi, this is Peter. And Peter Dragnev. Do you guys hear me?
Option. There is applause from the online audience.
Thank you.
So,
Alessandro, do you
one of
hear
the
me?
things is for the VC dimensions, right? As you explained, it's kind of related to some sort of linearity, right? Because you compute it as some sort of separating hyperplanes and so on, right? So maybe it's just for methods which are highly nonlinear, right? That might be just simply the wrong way to measure complexity. So when you have something like like some sort of linear classifiers and so on, then it makes sense to use a measure of complexity based on linear structures. But maybe for neural networks, that's not the way to go.
But wait a second. What do you mean that the VC dimension?
So I'm saying that this works well for these classical methods, right? Let's say when you have.
Oh, the VC dimension
Yes.
works. Oh, I see. Yes.
Yes.
Mm-hmm.
So when you go from something which is very nonlinear, it's just not the right way to measure it. The supernorm maybe is not the right way. The VC dimension is not maybe the right way. So maybe that's something you need something. There are people which work on that, but maybe that's not the direction to take.
So I know that, for example, one thing that has been worked on.
Oh, wait, there is a question from Professor Dragan, but no, we cannot hear him. Let me see what's going on here.
Yeah, I think I saw his screen being blue, but I didn't hear anything.
Uh-huh. Okay, so the question from Professor Dragnev, so Professor Dragnev, the chair of the department, is how are the random vectors Ri determined?
They are generated uniformly from a hypersphere in RD. So if we are in.
Let me see if I can fix something here. So let's try to talk again. Try again.
Oh, do you guys hear me?
Now we can.
All right. Well, I saw that they are uniform, but determining uniform points on the sphere is a difficult problem. How do you actually do it? Do you have a software that kind of gives you uniform points?
I was not very involved in the process of programming it, but I believe that my advisor with her previous students uses Gaussian coordinates for each coordinate. So it's a Gaussian random variable independently generated, and then some scaling. I think there is some result that says that it corresponds to a uniform distribution on this hypersphere.
So most probably optimizes some potential function or something, maybe with Gaussian potential, and then kind of minimizing and the minimum approach the uniform distribution. Is that?
I do not think it is that complex.
Okay.
I think I have to look into that. I believe that the generation of every coordinate according to a Gaussian distribution will be sufficient, but I need to double check that because you say that it's not. So I need to take a look at that.
Yeah, I guess the concern is how the process of randomly generated results affects your results after. Yeah, so if there is the way in which you I guess the concern there is if the way in which you generate those affects your bounds after.
With respect to the work, it does not have almost any consequences. I think because oh no, it does. It has consequences on the second part of the paper, the approximation part, because there I compute the probability of hitting a certain area on the sphere, and I use uniform distribution there. For the first part, for the generalization, the distribution that's used for generating vectors is not important, because then everything about the generalization gaps will hold the same way.
And my second question was, I saw you have a covering radius or covering number
Yes.
that you used. So you had like a fixed radius and how many points cover that ASD or whatever, that A sub D maybe said. Is that what you did? Are you trying to optimize these? Because this is another difficult problem, which is called covering, and Alessandro and I kind of know a little bit about it.
Yes, I think
You more than me.
I think I've seen a work during the online conference on covering numbers that was interesting to me.
Yeah. Not easy.
Because the centers of whatever you cover, you know, if it's with balls, when you move them, you can reduce the number of, you know, the covering number. Most probably that's what it is, the optimal covering number. Because
Well,
I saw you there.
we have an upper
use it.
bound, or we do not look for the optimal one. I think there might be something
Right.
more optimal. But what we're basing it on is that the structure of those dichotomies is very simple. So the points of the dichotomies, they will not lie wherever on the hypercube they can. They will lie in a line. So after one projection, I don't know, I think that for the matrix it's not useful, but if we have a certain number of points, I don't know, like 5 points, then they will lie in a line, because they're
Yeah, just shifting the ones
yes,
left.
it's just shifting one label at a time. So we can create a line after each projection. There are let's say two large n possible dichotomies, but those two large n possible dichotomies lie close to each other, and you can create a permutation so that the dichotomies will lie in such a line, and the distance, the Hamming distance between them will be always 1. So only one
This is always one between consecutive.
consecutive dichotomies, yes. And this simple line is easy to cover. I don't know if we are using an optimal way of covering it, but we are using a way of covering it. So for example, if R, so there is a certain scaling involved. So
I see. Well, thank you very much. Very nice talk. Thank you.
Thank you very much for the questions. I will think about the uniform distribution.
So it's a line. So any other questions? I have many others. I will still do a couple of hours after the talk. Any other questions?
I welcome any questions.
Okay. Well, thanks a lot for your time.
Thank you for inviting me.
My question.
Uh-oh.